I'm actually going to talk about a little bit about what I do for my research, but I realized that my poster discusses a lot of my research. So I decided to talk about today how the kind of methods of radiocarbon dating evolved and why we need statistics in it at all. And importantly, why we would need Bayesian statistics in it. So that's what I'm going to be talking about today. And I'll talk a little bit about my research at the end as well. So it all started with this guy, Willard Libby, and him and his colleagues realized in 1949, I believe, that radiocarbon dating was a thing. So how does it work? Essentially, living things absorb carbon. So when we eat or when we breathe, we interact with the atmosphere and we absorb carbon. And more importantly, we absorb the radioactive carbon isotope known as radiocarbon or carbon-14, you might have seen it as. And so what this means is, because when any of these living things die, this interaction with the atmosphere stops, then the radiocarbon within that organism starts to decay. And so Willard Libby and his colleagues realized that you could use the law of radioactive decay to date organic matter, so date the time between now and death. And the law of radioactive decay basically denotes that the number of atoms now is equal to the number of atoms at time naught to the power of minus lambda t. So lambda is derived from the half-life of the given radioactive element, so in this case radiocarbon. And so then when rearranged, we can find an age for a sample, so long as it's organic. So as I'm sure you can understand, archaeologists were ecstatic about this. This is really exciting because it means they can date lots of organic samples such as wood, bones, charcoal, grains. So when I initially learned about this, I just imagined it just being little animals and humans, but of course tools with wooden handles can be dated and food and things like that. So it was a really, really big thing. So understandably, it was such a revolution that Willard Libby won the Nobel Prize for Chemistry in 1960. So surely that's the end of the story. Everyone's happy, they've got their dates. But that would be a bit weird because I've got most of my talk left. So not quite. Turned out the physicists need some help and they turned to statistics for that. So to use the law of radioactive decay, we need to know the concentration of radiocarbon at death. So that was that N0 value. And we can calculate this if the levels of radiocarbon in the atmosphere stay constant, but they actually vary, and they vary a lot. So human activities, solar winds, things like that, it really affects the atmosphere in the carbon-14 concentration in the atmosphere. And what this means is they found that when they were dating known samples, so known organic samples where they knew the date already, and they were using radiocarbon dating to date them, the dates were off, and by quite a bit. So since the 1960s, an international working group called the INCAL working group have been working on modelling and then revising a calibration curve. So colleagues from Sheffield have in the past and currently worked on modelling this calibration curve, and the most recent one, INCAL 2020, was released INCAL 20 was released in the past year. And so what this does is it allows us to take a radiocarbon date estimate, X, that we get from the lab, and the error that the lab also gives, and calibrate it to calendar years so that we can actually get the right date. So here you can see on this image the calibration curve. So the calibration curve's in red. And as I'm sure you can see, there are three curves plotted there. The reason being is that radiocarbon dates are used to model the calibration curve. And as I've just said on the previous slide, they come with their own error. So what this means is that the calibration curve itself also has error. So in popular literature and for the rest of this presentation, the calibration curve is denoted by mu, and the error is denoted by delta. And so on the left-hand side in yellow, we have a normal distribution. So this is because we assume the radiocarbon dates to be normally distributed. And you notice that you'll have units BP. This is before present, where present is 1950. And that is how we measure all carbon and calendar years in radiocarbon dating. It's just good to have a set point for consistency for the labs to provide dates for. So importantly, you can see that when this yellow normally distributed radiocarbon date estimate is calibrated, you get this blue multimodal probability distribution on the bottom. And so we can obtain date range estimates for this using highest posterior density intervals, but we no longer get that nice, neat estimate with an error. We get date ranges, and they can be quite large sometimes, which not ideal for the archaeologists. So we've calibrated the dates. Is that the end? No. Reason why is because archaeologists can infer more information about the dates of the organic samples based on the order that they're found in the ground. So what this means is that so long as the site hasn't been disturbed, the samples lower down in the soil are older than samples found further up in the soil. And archaeologists are very skilled at looking at when it has been disturbed as well, and inferring relationships about the order of the true calendar dates of any samples that they've found. And this practice is called stratigraphy, and is very commonly used in excavations all over. And so this means we can use Bayesian inference. So hopefully I'm not kind of patronizing anybody, but just in case anybody hasn't done Bayesian inference before, you need a prior distribution and you need a likelihood function. And by taking the product of those two up to proportionality, you get a posterior. So a prior is just some sort of expert knowledge, and this may come from past experiments and past data, or it may come from elicited information from an expert. And there's lots of research that have gone into how to do that well. And then we have the likelihood, which comes from some sort of data. And then together we get our updated knowledge from this. So in the context of radiocarbon dating, we have our stratigraphy, which is our expert knowledge. And we have radiocarbon determinations for our likelihood. So this gives us a normal likelihood function. And this in turn gives us our calendar date estimates. And they tend to be narrower than if we hadn't included the prior knowledge. So this is really handy. So just more explicitly to state this, suppose we have n samples where the true calendar dates for sample I is denoted by theta I, then we let bold theta be the set of all of our calendar dates that we're trying to estimate. So as I've said before, we can assume this to be normally distributed. And note we have the mu function here. So this is the calibration curve, like I said before. And because xi is on the radiocarbon scale, we have to calibrate our calendar date to make that also on the radiocarbon scale. So then in turn, our likelihood function for all the thetas is the product of up to proportionality, the product of the normal likelihoods. And we have two errors. One is our lab error on the bottom here, and then sigma, and then we have our error from the calibration curve, which is delta. So that's just why you've got the two errors on the bottom. And like I said before, we have to calibrate our calendar date to get it on the radiocarbon scale. And then for our prior, we don't have an explicit probability distribution. What we use instead is an indicator function. So what this means is we let our indicator function be equal to 1 if it satisfies all of our stratigraphic constraints, and it's just 0 otherwise. So from this, if we take the product, we obtain our posterior. Now, if the indicator function was a probability distribution, this would be quite nice, especially if it was something like a normal distribution. That would be quite easy. Unfortunately, because it's an indicator function, it makes things more difficult, but there are solutions to address this. So you can use MCMC simulations instead. In particular, I've mainly used in the past Gibbs and some Metropolis Hastings algorithms to be able to simulate the posterior probability distribution. So there are methods to address that, but it does complicate it a little bit. So then we can introduce phasing to the model. Archaeologists often group contexts into phases. They do this based on samples being from similar periods in time. So it might be, for example, a settlement of a particular group of people. They might want to group all of those samples into one phase. And given D phases in a site, we can denote the start and end of phase J as alpha J and beta J, respectively. So alpha J is the older date and beta J is the younger date. And then all of the thetas will be within the alpha and beta boundaries. And if you let NJ now denote the number of dates in phase J, you have this new notation where you have theta ij cal bp, and then for I between n, j, and 1 now rather than n overall. So, and then you have j between 1 and d because you have d phases. So this phasing adds a hierarchical component to the model because we take our thetas now to have their own distribution where they're uniformly distributed between the phase boundaries. So we don't assume any knowledge about where they lie within the phase. We just know that they lie within the phase at some point, and we take that to be a uniform distribution. So this gives us our new posterior. So it's pretty similar to before. We have our indicator function here and the normal likelihood here. It's just that now we introduce our uniform distribution for the phase boundaries as well. So pretty similar, and again, the sampling's pretty much the same. It's just an extra step in the simulation to sample your alphas and betas. So why do we care about phasing? Archaeologists aren't actually that fussed about the individual candidates of samples. They don't really care about the kind of date of a grain, for example. They're more interested in phases of archaeological activity and estimating the start and end of these phases. So this theory has been established for as long as I've been alive, and the computational implementation of the theory has also been well established and well done. So software such as BCal and OXCal have implemented all of this Bayesian inference to allow archaeologists to input their prior knowledge and their dates. So what's the next problem? The next problem is that in 2001, Nichols and Jones realized that this model works really well for estimating thetas, but it has an adverse effect on the estimates of the phase boundaries, and this in turn affects the estimates of phase lengths. In particular, it affects the oldest and youngest phase boundaries overall in a group of phases. So we normally take our prior distribution for the alphas and betas to be equal to 1 because we have no knowledge about them at all, really. And this just represents prior knowledge that there is none, and so it's an uninformative prior. So if we let alpha D and beta naught represent the very oldest and very youngest phase boundaries in a group of phase boundaries for a site, and if we let S be the difference between the oldest and youngest phase boundaries, so the overall time spanned, we also need to let R be the length of all possible dates. So this is kind of outer boundaries, so we know that our oldest and youngest phase boundaries must be constrained within these values. And this may be taken to be 50,000, which is the length of the whole calibration curve, or it can be determined by the archaeologist. So this is data taken from the SHAG mouth in New Zealand. This was a site that the data has 6 phases and 7 dates. And this plot is for the uppermost phase boundary, so for alpha D or alpha 6. And you can see here that they have these really long tails that span over 1,000 years, which for an archaeologist is really difficult because this is lifetimes and lifetimes of kind of historical phases, and we want to obtain better estimates than this, essentially. So this is when we let probability, the prior distribution for alpha B to be equal to 1. So Nichols and Jones decided to investigate this. They thought this is a little bit odd, and is this what should be happening? So they found that the marginal posterior for S, so recall that S is the time elapsed between the very oldest and very youngest phase boundaries. They found that this was proportional to R minus S over S to the n minus 1, where m is the number of phase parameters. So not the number of phases, but the phase parameters, which is sometimes 2 times that or a little bit less, depending on the phase relationships. And so this means that a span of 2S is favored over S by roughly a factor of about 30. And you can see the Nichols and Jones paper for a full derivation of this. But obviously this is a huge problem because we don't actually have any prior knowledge of wanting to favor larger spans over shorter spans. So this was a kind of accidental implication of our model that we didn't want. So to counteract this preference for larger phase lengths, Nichols and Jones proposed this new prior distribution. And it's essentially the previous one flips, that it counteracts it and essentially makes probability of S, the probability distribution for S equal to 1, which is what we want. So in their paper, they so for R, they gave that as 500 years. And so to make it a fair comparison for the models, I've also capped the previous plot that I've just shown you at 500 years. So now it's capped between 950 and 450, just for a fair comparison. So this is when we let our prior distribution for alphas and betas be 1. And so this is what happens when we introduce the new prior distribution. So you can see that it's much more peaked, and there's hardly any probability of the older values for the uppermost phase boundaries. So it's had a real difference to the uppermost phase boundaries, and it does affect the lowermost phase boundaries as well. For this particular model, because the lowermost phase boundary is so close to 0 on the calibration curve, you can't really see the effect. So that's the only reason I've omitted it today. But usually you can see the same behavior in the younger phase boundaries as well. And so modeling S, so the posterior probability for S, we can see that the top one is when you use the prior distribution for alpha beta to be equal to 1. And so you can see that it's much less peaked, and there's probability around kind of 300 and 400 here. So these are kind of feasible phase durations. Whereas when we introduce what I call the squeezing model, because it kind of squeezes it up, but when we introduce Nichols and Jones alternative for the prior and alpha beta, you can see that it's much more peaked around the smaller values, and actually there's hardly any probability that the phase duration was longer than 200 years. And again, you can use highest posterior density intervals to obtain estimates for this. And so what this means is that archaeologists if you use this model, you accidentally get almost incorrect phase lengths because of this spreading effect of the model. And so this is not what we want. So now this kind of squeezing model is implemented within BCal and OxCal so that doesn't happen, and archaeologists can obtain better estimates. So where next? This actually leads to my research, which is, as Caitlin was saying, funded by Historic England and also the Arts and Humanities Research Council. So a bit weird for a maths PhD, or statistics, should I say. But archaeologists don't always agree. So if we kind of go back to that indicator function in your mind, which was 1 if it satisfies some sort of stratigraphic constraint, they don't always agree on these stratigraphic constraints. This is subjective knowledge, and it depends on the person excavating what they decide that is. And if people disagree, what do they usually do about it? They kind of fudge it. I hope no archaeologists are in this call and are offended at me saying that, but they just kind of say, single model's fine, and we're going to assume this one's correct, mine's correct, and we're going to use that. So my stratigraphic constraints are correct, essentially. So the purpose of my PhD is to build software to allow archaeologists to build multiple plausible models, so consider multiple prior models and hence multiple prior stratigraphic constraints, and then assess the suitability of these models as well. So what do we have so far? We currently have a prototype graphical user interface, and this uses mathematical graphs to allow users to model their stratigraphy. So the layers of soil are represented by nodes, and then the relationships between those are represented by edges. And what we plan to do next, so the focus, I'm actually on leave of absence at the moment for a job role, but when I come back in October, the mission is to test the software with the user community. So as I've said before, I'm not an archaeologist. I come from a mathematical and statistical background. So I want to test the software and find out what works for the user community and what doesn't. I also need to debug the software because I also don't come from a computer science background. So although I've given it my best shot at building an application, it definitely needs some debugging. So that will be something that I'll be working on towards the kind of end of my 3rd year. And then the final bit, which is a bit I'm excited about, is investigating model selection metrics. So currently, the model selection metrics that are used, everybody, I think, in the community would admit that they're not suitable. They tend to assume that there is one correct model, and that's not the case. So at the moment, there's some potential routes of investigation that we want to look into, but my main focus for my 4th year will be investigating model selection metrics for these wide range of very complex prior models in archaeology. So I'll leave it there. If you're more interested in the kind of mathematical graph stuff, please look at the poster. Hopefully that explains it well. Otherwise, you can email me. And if you want to look at my very buggy application, it's also on my GitHub if you're interested. And these are the two kind of main publications that I've referenced throughout the presentation. Thank you.
Thank you very much, Bryony. Another perfectly timed talk. I don't know how you young people manage it so brilliantly, but it makes the rest of us have a lot to live up to. So thank you very much indeed. Okay, so the same protocol as before. If you'd like to ask a question, please pop something in the chat. And you can either speak, you can ask to speak and we'll let you do that, or you can post your full question in the chat and we'll try and answer it. And since that might take a bit of time, I will start. So Bryony, at several points you talked about zero age, I think you said, or naught on the time scale. And I think some people might be rather confused about that because most timescales that we work on usually don't have a naught.
Yes, so this goes back to right at the start of the presentation when I mentioned that it was in Cal BP. So before present was 1950, so we take 1950 to be naught, and then going back in time, that's as the dates increases on the BP scale, which is why the histograms look kind of flipped. So you have 0, all the smaller numbers on the right-hand side, and then the older numbers on the left-hand side. So yeah, thank you for bringing that up, Caitlin. Sorry if that confused anyone.
Yeah, so you've been drawing things so that time goes from left to right, is that correct?
Yes.
Yeah, so old things are on the left of plots, all right, okay. I guess
yes, the older it is.
Good, okay. Since I can't see anybody else typing questions also, perhaps you could say a little bit about what kinds of model selection tools are out there. So you said the ones that exist currently are not very good for this problem. Can you say, yes, can you say anything about what you're going to be thinking about in the way of approaches?
Yeah, so at the moment, what's kind of out there tends to be based on Bayes factors or pseudo Bayes factors. And as I said before, they assume that there is a definite kind of correct prior model within your set of prior models. And so instead there are, so it's Williamson and Goldstein are two chaps who are working on model selection for an infinite number of prior models, which we don't have to consider an infinite number, but you need to consider a huge amount of prior models in this potentially, just because of the sheer amount of samples and context that you have. And so what they also assume within their theory is that you don't have to have a correct model within your set of prior models. And what's also interesting about their theory as well is that, I forgot where I was going with this. I got focused on the no correct model. Oh, yeah, so it's not a comparison between the likelihood and the data. So I need to look more into this. This is something that I was kind of just getting to before I went on my leave of absence. But it seems like a really flexible approach. And it's not kind of black box comparison. It's fully kind of mathematically defined, which I'm really interested to really get into how to apply it to this problem, because they've applied it to the oceanography, I think, so ocean data, and also they've looked into the idea of it for food networks, but not archaeology yet. So it'll be interesting to look into its applications for archaeology.
I mean, it seems to me that this is an area that we collectively as mathematicians and statisticians probably don't place enough focus on, because all of us build models of some sort, and I think we would struggle, most of us, to answer the question, how good is your model? We have this common phrase, all models are wrong, some models are useful, that kind of thing. But actually, maybe we should be beginning to try and put more thought into how we might quantify the reliability or appropriateness of a selection of models. So I think it's going to be a really interesting part of the project, and I look forward to seeing where it comes from. Okay, so there is another question now for you from Joseph Kutajar. He's asking, as regards the first page, is there a restriction on the value of lambda? So this is in the,
So, I mean, I don't want to say for sure. I'm pretty sure it's just the half-life, but I feel really bad if that was incorrect. So it's either some variation of the half-life, so the half-life multiplied by some scalar, or the half-life. So when it comes to radiocarbon dating, it's restricted by what the half-life value is. And we actually take an old estimate for the half-life. I say we, I don't work in a radiocarbon lab, but they take a older version of the half-life rather than more updated estimates to be the half-life that they use for the radiocarbon dating, just because then there's consistency with older samples. So it's either the half-life or some scalar of the half-life.
That's right. Yes. Yeah, it's a rate. But
yeah.
So let me think about this for a minute. So yeah, that's right. It's a scalar of the half-life. And the point is that Willard Libby, that was a really big contribution of Willard Libby's work, was that he and his team estimated the half-life, which was a very big undertaking at the time. And unsurprisingly, they weren't quite right. later estimates have been provided. But as Bryony says, because we want to be able to compare dates between years. Yeah, so the half-life is calculated by observations in the physics laboratory in the same way that other observations about radioactive disintegration are made. So basically, they observe the decay over time, and they make an estimate based on the available samples. So you might watch the decay over a year, say, and then use that to estimate the half-life. Of course, and because the half-life of these samples is long, the initial estimates were very poor. The longer you observe it for, the better your estimate becomes. Okay, so so because we have to calibrate all the radiocarbon dates anyway, that half-life estimate that Willard Libby provided has never been updated. We still use the same one, and that means that all the radiocarbon dates that have ever been made are all using the same half-life, so they can be compared one to another. So that was a very smart decision made early on, long before I got involved in any of this, because otherwise we would have this problem that every single radiocarbon date was calculated with a different half-life, which would be a bit of a problem.
Making it even more complicated than it already is.
Than it already is, exactly. So they are, in some sense, Ocean, they are all wrong. Ocean is saying, so they can all be wrong. Yes, is the point. The radiocarbon estimates as provided by the laboratory in their raw state are wrong. In an absolute sense, they're wrong. But it's known that they're going to have to be calibrated. And that correction is included in the calibration process. So when we calibrate radiocarbon dates and we use them in archaeological research, that along with everything else is fixed, basically, along with all the other problems that Bryony summarized. They're all solved all in one go by mapping from one scale to the other in the correct way. Great. Thank you, Ocean. That's a really good question.